All right, hello again, everyone. We are in 10.2 with patterns and inductive reasoning. So hopefully you have pulled up the notes packet. I have an entire PDF packet that goes through 10.2 all the way through 10.4. So hopefully you have that in front of you right now. So you have these blanks right here once you get beyond the first page that talks about what we're doing in this chapter. So these blanks are filled in with these words right here. Inductive reasoning is based on patterns that we can observe. It's inductive because we induce what we see. So please make sure that you work through the problem 1 on Pearson so that you can then deal with the got it. But let's just go ahead and look at these to make sure that you understand what you're doing. So if we're looking for a pattern, we can see here 3 to 9, my change is 6, and then 9 to 27, my change is definitely not 6. So let's go back and look at a change that would not be addition. If I go from 3 to 9 and think about the multiplication, that'd be times 3. If I go from 9 to 27 and think about the multiplication, that'd be times 3. And from 27 to 81, that's times 3. So we know that the next two terms in my pattern are going to be times 3 of the previous term. So take a second, figure out those next two terms, and then come over here. We have a circle with a triangle, then a circle with a square, then a circle with a pentagon. See if you can figure out what the next two shapes would be. So for B, hopefully you notice that the pattern is that the shape is getting one more side, or the shape inside the circle is adding one more side every term we go in the pattern. So then we'll have a circle with a hexagon and then a circle with a septagon, or a 7-sided polygon. All right, guys, so we are on the got it for problem 1 here. You see you have a numerical sequence that you want to find what are the next two terms, and then you have a geometric shape sequence that you want to find the next two terms. So pause the video and try that. So my arithmetic sequence up here, you can see we are reducing by 5 every time. So my next two terms would be 25 and 20, and we could even keep going because that would be really easy. And then my geometric figures down here, you see that there's a square, then there's 2 squares, and my middle one is rotated by 45 degrees, then there's 3 squares, my middle one is back straight again, then my 4th term would have another one rotated in the middle, and my 5th term, if I drew it out, would have this same exact shape with yet another square in the center there. Go ahead and try the practice here, make sure that you are doing well because this arithmetic is a little bit different as well as this geometric. So pause and try those for a second. So when we look at what's happening, we're really halving our values, or you can think of my denominator is getting doubled. So here this would be 1 over 1, 1 over 2, 1 over 4, 1 over 8. So now I have 1 over 16, and my apologies for not being able to write fractions very well on the computer. And then I have 1 over 32 because my denominator just keeps doubling. What I would see down here for the geometric figures is I continually have a hexagon, but I start out with dark red kind of pointing, I sometimes like to use north, south, east, west, so it's kind of pointing northwest, then it's pointing directly north, then it's pointing northeast. So then on the next one it would rotate again, and your dark red would be here, your light red would be there, and your blue would be up top, and then it would rotate again for the last one, and your dark red would come down to the very bottom, your light red up at the top left, and your blue at the top right. I can't really draw those on the computer, but that's what it would look like. Now you've probably heard this word before, but the next vocab word we're going to talk about is a conjecture. So a conjecture is a conclusion that we reached using our inductive reasoning. So remember, inductive reasoning is based on things that we see. So if I look here at how diameters relate to how many different regions of the circle I have. So the question that we're being asked is, look at the circle, what conjecture can we make about the number of regions that we get based on a certain number of diameters? So if I compare my diameters, I have 1 diameter, 2 diameters, 3 diameters. 1 diameter gives me 2, 2 diameters gives me 4, 3 diameters gives me 6. So if we look at the relationship between the number of diameters and the regions formed, you can see that the regions formed is always going to have a relationship, that of double the diameters. So if I have 20 diameters, then how many regions would it form? You would be absolutely correct if you said 40 regions. So there we go. We will move on to the got it of problem 2. So if we saw this pattern, and we have RWB, which I like to assign words or values, so I would say red, white, blue, red, white, blue. So I see that I'm kind of cycling through these colors. We continually, maybe this is how a candy machine spits things out, or you could assign a lot of different real world situations. But since I have red, white, blue, and those are terms 1, 2, 3, 4, 5, 6, we then have to figure out what will be the 21st term. Well, my first term is red, but then I have a cycle of 3. So think about taking 21, dividing by 3, and figuring out would I be at my first term, my second term, or my third term at term 21. So take a second to think about that. So what you really want to pay attention to is, since that 21st term, 21, is divisible by 3, you want to look at the other terms divisible by 3. So third term is divisible by 3, the sixth term is divisible by 3. So what we see is that every third term is a B. So since 21st would be a third term, it's divisible by 3, we know that that term would be a B. So now down here in practice problem 3, that doesn't work as easy, because what we're being asked is to find the 13th figure, or sorry, the 30th figure. Misspoke there for a moment. So since it is 30th, and that is not a prime number, it's convenient. We can go ahead and say I can figure out the 30th term based on it being divisible by 3. So since it's divisible by 3, we can look at every third term. So we see a square as my first third term. Then 4, 5, 6, I have a triangle. Then if I did square, star, circle would be my next one. So I would see a circle, so I'm going to go ahead and draw that. So the pattern that we can notice is every third term is actually working its way backwards through the pattern. So we had a square first, then we had a triangle, then we had a circle. So notice square, triangle, circle. So then the next one would assumably be a star. Then it would be a square again, then a triangle, then a circle. So we really, since we're looking for the 30th term, we're looking for the 10th third term. So if this would be 1, 2, 3, then my fourth one would be a star, my fifth one would be a square, sixth would be a triangle, seventh, eighth, ninth, and we can assume that our 10th term here would be a triangle. So we get a triangle for that one again, just to restate, but I'm going to then erase all my highlighters from that one so that I can use green for the new problem. So just like that problem was divisible by 3, so we'd look at the third term. Because this, we're looking for the 40th figure, we will look at the fourth terms. So let's start that process by saying 1, 2, 3, 4, I begin with a star. Then 1, 2, 3, 4, I have another star. And what I can notice is that I only have 4 different shapes, and the shapes are going in order: circle, triangle, square, star, circle, triangle, square, star. So that pattern is going to continue to repeat itself. So your 40th figure will in fact be a star. So hopefully this all is making sense to you. We are going to move on into problem 3. So please make sure you go and work through the Pearson module and then come back for the got it. So actually, I will help you out with problem 3 if you have had any issues. If not, you can skip ahead and find where I pick up and find the got it. So we want to make sure that we gather data before we make a conjecture. The more information that you know, the better that your conjecture will be. So if we're looking at a table of terms, and we see that we have 4 terms and then the sum of the terms, go ahead and try to analyze all this information that we have. So this is one of those really cool sequences that ends up with a rule that is, very fun. So first term, you only have the first even number. So you have 2 equal to 1 times 2. I mean, you wouldn't think to write it like this to begin with, but as you get bigger and bigger up, you see that the second term could be written as 2 times 3. And the third term, 12, could be written as 3 times 4. And the fourth term could be written as 4 times 5. So what we're noticing here is that this pattern that we see is it is the term number times the number after it, or the next integer. So our conclusion is that for the 30th term, we'll do 30 times the number after it, and find that our value is 930. So on the got it for problem 3, we're looking at what conjecture can we make about the sum of the first 30 odd numbers. Now, odd, just like even, makes a fun pattern, but it's kind of hard to see. So when we look at the first term, it's just 1, and that doesn't really help us very much. When we look at the second term, it's 1 plus 3, gives us 4. Third term, 1 plus 3 plus 5 gives us 9. Fourth term, 1 plus 3 plus 5 plus 7 gives us 16. And as we start to look at all these terms, a pattern should start to appear. You should ask yourself, how does 1 relate to 1? How does 2 relate to 4? How does 3 relate to 9? How does 4 relate to 16? And all these relationships have to be the same. Some kind of addition or multiplication or power. So the relationship that we see here is that we are taking the term number and squaring it. So 3 squared is 9, 4 squared is 16. So what we can tell is that all it will be is the term number squared. So the sum of 30 terms is just 30 squared, or 900. So now looking at practice problems 5 and 6, take a moment to pause the video and try it on your own if you have not done so yet. We can actually use one of our previous conjectures to deal with the first 100 positive even numbers because we already saw that even numbers, when we're dealing with their sums, is just the even number that you're on times the number above it. So not the even number above it, but just times the integer above it. So this would be 100 times 101. So the value that we then get is 10,100. Now the product of two odd numbers, you might want to try some examples with that first. So you can look at, like, let's say 3 times 5 equaling 15. You can take an even easier one, like let's say 1 times 7, which would just be 7, or 3 times 7, which would just be 21. What we notice about all these values that we're getting when we're multiplying two odd numbers is we're asking for an odd number of odd numbers, which will give us, in the end, an odd number. So our conjecture that we can make is that the sum, or the product, will always be I'm going to pause for a moment. So what we can say is that the product of two odd numbers will always be another odd number. So the part 4 got it relates to the problem, so please make sure you've worked through the problem in Pearson. So to look at the conjecture of backpack sales in June, we want to look at our graph and see we have January, February, March, April, May, so June would be out here somewhere. And what we see is that we have a trend line of decreasing sales, and if I try to look at how that's decreasing, it's approximately 500 less each month. So we could say that June will be approximately 500 less than May, and May would be approximately 8,000. So for June, we could say it'll be about 7,500. Now, when we think about reasonable to use this for sales in August, remember, we go back to school in August, and August is back to school shopping time. So since we know that November has really high backpack sales, we know that at some point these sales are going to start to increase again. So this would be kind of dangerous to use to make a conjecture about August. Now, counterexamples are always fun because a counterexample is an example that shows a conjecture is incorrect. This is how you can win an argument. So if you are looking for counterexamples, and I'm running out of time, so I'm going to be moving fast, a counterexample to each of these. So go ahead and think. If the name of the month starts with the letter J, like June or July, it is a summer month. What would be a counterexample for that? If you connect any 3 points to form a triangle, is there a counterexample for that? When you multiply a number by 2, the product is greater than the original number. So here are all my counterexamples. For a J month, January is not summer. For connecting 3 points, I can make a line, or we could just form an angle. And this conjecture only holds true for positive values because if my original number is a negative, then my resulting value is not bigger than the original. It is actually quite smaller. That is all the time I have for this topic. So please make sure you've worked through all of the Pearson module, done your homework, and let me know if you need any assistance. Thank you and have a great day.